In this video, we're going to talk briefly about some of the material at the beginning of Chapter 2. In particular, we're going to talk about computer capabilities, the processors within them, what those processors can do, brief discussion of formulas versus algorithms, and the role of algorithms in implementing intelligent behavior. So in the previous slides in this series and the first few pages of the book, we talked about the various ways that we can implement computational functions using mechanical methods or biological methods or electronic methods or quantum mechanics. So the bottom line is there's quite a few ways in which we can build what we might generically call an automated computation device. Okay. Now, just because an automated device can do computations does not make it a computer, at least by the modern definition of that term. Okay, so we have a situation where we have a class of devices that do automated computation, but there's a subset of those devices that are in fact computers. So what distinguishes one from the other? Well, there's just a few things, but they're very important things that we're talking about here. The first is the concept of a general purpose processor, which we'll get to in a bit more in the next slide. But the concept of general purpose basically means that we can use this to do multiple things. So one minute we can use the processor to surf the internet, the next minute we can use it to do complex mathematical calculations for, I don't know, helping on our math homework or whatever. The next minute we can be using it to view pictures and manipulate them, making them darker or lighter or what have you. Okay. So there is a general purpose processor. Yes, it does perform computation, but it also performs some other things that we call logic functions, which we'll explore a bit more in a minute. And that general purpose processor can change the mix of these functions it performs depending on our needs. The next thing it needs large amounts of storage for instructions and data. Okay, your basic, a simple automated computation device. Here, let's back up a minute. I mean, here's your original mechanical computer, or one of your original mechanical computers, the Babbage difference engine. This actually isn't the whole difference engine. This is just one piece of it. But your storage capacity here is fairly limited. If you notice these numbers kind of facing you from these dials, I mean, that's basically the storage. And if I look down or across these columns and see which numbers are displayed, that is the number. That is the contents of its memory, so to speak. Well, there's not that many of these dials here, so therefore there's not that many digits that can be stored. And of course I can sit here and crank this handle a few times and these digits will change, but the number of the wheels that display those digits is not going to change. So the storage capacity of this device is relatively limited. Okay, and since that we're using essentially the same wheels to both store and output, because we can look at the numbers on those wheels, both the storage capacity and the output capacity are relatively small. Okay, so in a modern computer, of course, we expect to be able to store, gigabytes or petabytes or exabytes worth of data. We expect to be able to store large numbers of programs and instructions. Okay. The last thing that differentiates a modern computer from a more basic automated computation device is communication flexibility. So, for example, let's take just your basic calculator. Your $4 or $5 solar-powered calculator that you might buy at the Walmart and stick in your car to compute your gas mileage. Okay, you've got a relatively limited number of ways to get data in there. You've got 10, 12, 15 keys on the front of it, all the digits and plus, minus, and maybe a memory key and clear key and things like that. So you've got a fairly small keypad, and that's the only way to get input into the device. And then, of course, you got some kind of display, usually a liquid crystal or something like that can display, 8 digits, 10 digits, 12 digits, and that's your output device. And that's pretty much it. Okay, so you interact with it by, pressing the keypad. It interacts with you by displaying something in that liquid crystal display. And that's the extent of its flexibility. Compare that to a typical desktop computer where you have a mouse, you have a keyboard, you might have a microphone input, you've got a network interface, you've got a display, you've got a set of speakers, you've got USB ports, you've got a lot more devices that can be used to put data into the computer or get data out of the computer, and they're of various types, so there's much more flexibility there. So in sum, what we look for in a modern computer is a general purpose processor that can do lots of different things, a large amount of storage and instructions to back that up, and an array of communication devices of various types that gives us lots of flexibility for communicating both with humans and with other computers over some sort of network. All right, on to computer processors. So at the heart of a modern computer is a device called a processor. We might call it a microprocessor, we might call it a chip. And that processor has some basic capabilities, and here we've divided them up into three categories. Okay, later on in the book we might actually delve into these a bit more deeply. The first category is computation. So this is after all called a computer, so we expect it to do some computing. And of course we've got the basic set of just add, subtract, multiply, and divide, but there are other more complex things like powers and roots and logarithms and trigonometric functions and so on that might be built inside this computer. We won't discuss it until much later in the book, but the fact is you can do an amazing amount of complex computation with just these four capabilities. Okay, add, subtract, multiply, and divide can be combined in some pretty creative ways to do much more complicated things. And as a matter of fact, going back to the Babbage difference engine for a moment, this is an example of a device. Really, the only thing this device does is add, but it is constructed in such a way that its addition capabilities are combined to enable it to do more complex functions. Basically, what this device was designed to do was to crank out tables of numbers representing complex formulas. Things like tables of logarithms, things like tables of trigonometric functions, things like tables of astronomical functions. So, but its basic computational ability is addition. Okay. Now we're not going to get into detail at this point about how you take addition, combine it using these complex wheels, and get it to do trigonometry. But the bottom line is it's possible. Just take that on faith for the moment. So although you may not think of add, subtract, multiply, and divide as being particularly powerful, it is in fact quite powerful, particularly when you can do it with 100% accuracy at a rate of billions of computations per second. Okay. The second class of things that processor can do is comparison operations. It can take any two numbers and tell you if one is less than or equal or greater than or not equal or less than or equal or greater than or equal than another. Okay, and we'll come back to that in a couple slides, but that becomes the basis of something we call an algorithm, which is in turn the basis of mimicking at least intelligent behavior. Third class of things that processor can do is it can move data, numbers, from one place to another. It can move them from one memory location to another. It can move them from, say, memory to a mass storage device like a disk drive or a flash drive. And it can move back and forth to I/O devices, such as grab information from a keyboard, put it in memory, do some computations and comparisons, compute some other numbers, store it on a disk drive, or send it to an output device so that you can display it. Once again, a lot of communication flexibility, and that communication flexibility comes not only from the variety of I/O devices and of storage devices, but from the ability of the processor to move data freely among them and among internal memory locations. Okay. Now, when we look at how these capabilities are combined to do something useful, we come to the concept of a program, and that's described here on the last bullet. Complex tasks are accomplishing by combining many instructions into a program and executing the program. If you flip forward a couple of slides, you'll see an example of a program here on the right on this slide entitled Algorithm Example is an example of an old style BASIC program. Don't try typing this into your modern Visual Studio because it won't know what to do with this. But this is an example of a basic program that implements the algorithm or computation that's inherent in this tax table here on the left. Okay, so this is a sequence of instructions that is just laid out from one to the end. Okay, and each of those instructions tells the computer to do something relatively simple. These aren't quite processor instructions, but they're pretty close to it in terms of level of detail. So now that we've seen one example of a program, let's back up and talk about the specific components of it. So it doesn't quite work, but you might think of each line of that program as being an instruction. Okay, it's a command to the processor to perform one specific function, to add two numbers or subtract two numbers or divide two numbers or compare two numbers or move a particular number from one place to another. Okay, now the fact is some of these lines, or actually most of these lines, may in fact wind up being multiple instructions. So for example, take number 20 here. If income is greater than 7150, then go to line 50. Well, there's at least two different things going on here. The first thing that's going on here is we're comparing two numbers. Whatever the number stored in the memory location that we call income is, we're comparing it to this constant 7150 to see if income is greater than 7150. So that's one instruction from the processor point of view. Depending on the result of that comparison, whether it's true or false, we will then alter the instruction sequence of this program by either going to line 50, which would skip over 30 and 40 and take us to this next if statement, or assuming that that comparison is false, we'll simply fall through and execute line 30, which does a computation. So there's actually two processor instructions embedded here in line 20, or at least two. It might be more depending on the particular processor. Okay. So our program is a series of instructions to the processor. Each of those instructions does one of these three things. Okay. Each of those instructions is relatively simple or primitive. Okay. And when our general purpose processor, quote unquote, follows one of those instructions, the terminology is it's said to execute the instruction. Okay? And of course those instructions are combined to form something we call a program. All right, let's come back to this this concept of a general purpose processor versus a special purpose processor. We needed to at least get somewhat of a handle on what a program is before we could distinguish between these two. Okay, what makes a general purpose processor a general purpose processor? Well, the most important thing is that it reads its program instructions from a storage device and that the contents of that storage device can be changed. Okay, or another way of thinking about it is think of lots of different programs being stored on the storage device, and the general purpose processor can read its program instructions from different parts of the storage device, therefore reading different programs. So think of the hard drive on your laptop or your desktop, or even think of the apps that are stored in flash memory on your cell phone. Okay, that flash memory on your cell phone is a storage device. It holds hundreds or thousands of different programs, each of which is just a sequence of instructions. And when you pull up your menu and you click on one of those little icons, what you're doing is you're telling that general purpose processor, go grab the program at this particular part of the storage device, load it into your memory, and then start executing those instructions. Okay. Because the content of the storage device can be changed, or another way of thinking it, because we can point the general purpose processor at different parts of the storage device, okay, we can change the behavior of the processor. Okay, the processor does what the program tells it to do. If we can change the program either by reading from a different part of the storage device or by overwriting the contents of the storage device with a new program, then we can change the behavior of the processor. That's what makes it general purpose. It can do multiple things, okay, different things. Okay. Contrast that to a special purpose processor. Okay. Now, a special purpose processor does one thing. Okay, maybe a complicated thing, but it does exactly one thing. Now, there's two ways to build a special purpose processor. We've got kind of the old-fashioned and the new-fashioned way. The old-fashioned way is the second one I have listed here. And when I say old-fashioned, here I'm probably talking from, say, the late 50s to the early 90s. Okay. The idea here is that we construct the processor such that the instructions of the program are literally wired into the processor. Now, of course, here I'm talking about electronics, but it could just as easily be a mechanical device. So once again, let's go back to this Babbage difference engine for a minute. Oops, keep having trouble finding that. Okay. What we have here is a device that does nothing but add. Okay, the primitive components are all addition modules or addition circuits, if you like, but these aren't circuits, of course, because they're gears, not electronics. And they have all been connected in such a way that this device does a very particular kind of, or a very particular set of additions in a very particular order. Okay. Now I can vary the input value that it starts from. I can take this left column of wheels here and I can set those to a particular starting value. But once I start turning this crank, the mechanical relationship between all these wheels downstream is fixed. I can't vary what's going to happen. Okay, so these are going to add up and it's going to generate these, and then these are going to add up and it's going to generate those, and so on and so forth. And I can sit there and crank as many times as I like, but each time I crank, I'm basically doing the same thing over and over and over and over again. Okay, that's the essence of a special purpose processor. If I want to change what this thing does, okay, it's not as simple as saying, well, I just load in a new program. The processor is the program. Okay, the two are indistinguishable. I have literally constructed the device in such a way that it is a physical manifestation of the program. Therefore, this device can only ever execute that program. If I want to execute another program, I have to go build another device that is constructed differently in whatever way that other program would imply. Okay. So literally, one way to construct a special purpose processor is to literally build a device that implements it. Okay. And if you were to look, say, inside the very earliest computer-controlled engines, okay, where you had a very simple processor that measured the amount of oxygen that was being read by a particular sensor, and if that fell below a certain threshold, then it moved this particular valve in the intake manifold and maybe changed the timing of the engine, or reduced the spark or increased the spark. And if the sensor was, if the value coming in for the sensor was the other way, then it did something else. Those processors were literally engineered as custom designed electrical circuits. Okay, and once they were designed, they were manufactured like any other chip at the time, packaged into a little chip that was put on a circuit board, and that was installed inside the car. Once that chip was manufactured, put on the circuit board, installed in the car, it would do the same thing over and over and over and over again for as long as you drove the car, but it could never change what it did. That's a special purpose processor. Now, along about the 80s or 90s, what happened was people realized this was not necessarily the most efficient way to do things. And the reason it's not the most efficient way to do things is because if you have to change a program by changing an electrical design and then you have to build a new chip to match that electrical design, well, it's relatively expensive to design a chip and move it into manufacturing. Okay, the way you quote unquote recover that expense is by making lots of the chips. So you spread that expense across, millions or tens of millions or hundreds of millions of units. But let's say we're talking about the, oxygen control chip for pick a car, a Chevy Impala. Well, if I'm only going to make 50,000 Chevy Impalas in a year, well, then I've only got 50,000 units over which to recover those fixed costs of designing and manufacturing that chip. Okay. The contrasting approach is to take a general purpose processor. Okay, so let's say instead of custom designing a processor that does this one particular function, I take a general purpose processor that's powerful enough to do that process. Say like one of the very early processors used in microcomputers, something like a Z80 or an Intel 8088. Okay, Intel's out there cranking those out by the hundreds of thousands per month, and they can sell them fairly cheaply because they've manufactured a lot of them. They've designed it once and spread that design and cost over millions and millions of units. So what car manufacturers started doing, and just about every other manufacturer that needed quote unquote a special purpose processor, is instead of custom building chips to do with the programs quote unquote wired in, what they would do was buy a special purpose processor. That special purpose processor would read its program from another chip, generically called a read-only memory. And since that program was the only program on that chip and was pretty much burned in there, that general purpose processor now acted like a special purpose processor because it only had one program. If you only give the general purpose processor one program, and that can never be changed, then you have in essence turned what is physically a general purpose processor into a special purpose processor. Now the other thing that kicked in here, this idea of building custom chips made a lot of sense when processors were relatively slow, because sometimes you could get a performance boost by doing the special purpose processor. But as the general purpose processors got faster, that performance boost became less and less important, particularly compared to the costs of producing these special purpose processors. All right, so I probably spent too much time on that, but the basic idea is that if you're going to call it a computer today, it better have a general purpose processor, and that general purpose processor had better have at its disposal a whole bunch of storage from which it can read lots of different programs and therefore alter its behavior depending on your whims. Am I writing a term paper now? Am I playing a game now? Am I reading Facebook now? Those are different programs. Okay. And so the general purpose processor can switch back and forth amongst them simply by loading in a new program and following that instruction set. The special purpose processor can't do that, either because it only has one program that it can read in, or because the program is literally built into the processor. They are one and the same. Okay, which brings us to the next topic, which is the issue of formulas versus algorithms. Once again, back to the Babbage difference engine. Okay, the relationship between these rows of wheels is in essence a formula. Okay, and it's a pretty complicated formula, and I'm not going to write it out for you. You can go look it up on Wikipedia if you like, but the bottom line is it is a formula. Okay, so what do I mean by a formula? Well, let's come back to this slide on formulas for a second, and let's pull up a very simple example, which is where? Oh, there it is. Okay, so here's a couple of formulas. Okay, my first one. So if I want to compute miles per gallon that I realized as I traveled based on my last tank of gas, I need to know two things. I need to know how far have I traveled since I last filled up, and how many gallons have I consumed, which, assuming I filled up, simply means, how many gallons did I put into the tank at the last fill up. So if I know the distance traveled since the previous fill up and this one, and if I know how many gallons I just put into the tank, I take the distance traveled, I divide it by the gallons consumed, and that gives me the miles per gallon. So for example, if I made it 200 miles between the two tankfuls, and if I just put 7.5 gallons into the tank, I divide 200 by 7.5 and find out that my miles per gallon in the last tank was 26.666666 ad infinitum. Okay, that's an example of a formula. Okay, it's a mathematical, relationship which can be reduced to a specific sequence of instructions. Okay, get this number, divide one by the other, store or display the result. Okay, that's the sequence of instructions. Okay. The thing that makes it a formula is that the same instruction sequence works regardless of what the data input values are. Okay. So this miles per gallon formula works for your little, Subaru Forester or your little Toyota Camry or your F-150 pickup truck. It even works if you're driving one of these giant dump trucks like they use to, bring out God knows how many tons of ore from an open pit mine. Now, clearly the numbers are going to be different. If we're talking about that giant dump truck, maybe the distance traveled from the bottom of the open pit mine to wherever it dumps it is only 2 miles. Maybe the gallons it consumed in that process was 25 gallons of diesel fuel. Okay, but the bottom line is it's still two numbers. You still do exactly the same division to generate the result miles per gallon. Yes, for your little Camry is going to generate 26.6. The one for that big dump truck's maybe going to generate 0.12. But it's exactly the same formula, the same instruction sequence, regardless of what the data values are. Okay. Ditto down here with converting Fahrenheit to degrees Celsius. If I take the degrees Celsius as input, say 100, run it through the formula, note this is just a little more complicated than the one above, I'm going to come up with the equivalent degrees Fahrenheit. It doesn't matter whether degrees Celsius is a single digit number or a 50-digit number. It doesn't matter whether it's positive or negative. It's always the same formula, always the same sequence of instructions, over and over and over and over and over and over again. All right, so what about an algorithm? Okay, well, an algorithm is more complex than a formula. Okay, and what makes an algorithm different than a formula? Okay, yes, it is an instruction sequence. Okay, but it's an instruction sequence where we can literally alter the sequence depending on the data input that's put in. Okay. So for example, we may have a formula, or say we have two formulas, okay? And we use formula number 1 if the input value is below 100, and we use formula number 2 if the input value is 100 or more. Or maybe it's, formula 1 if the value is 0 or positive, and formula 2 if the input value is negative, okay? So think of each formula as a different instruction sequence depending on the data input characteristic, less than or equal or greater than or equal to 0 or less than 0, we change the instruction sequence. We choose formula 1 or formula 2 and quote unquote use or load the appropriate sequence that goes with that. Okay. Now, from the point of view of a computer processor, how can I vary instruction sequence? Okay. Well, in order to vary instruction sequence, I have to do what we call in programming evaluating a condition. Okay. So for example, in the example I just gave you, the condition was, is the data input value greater or less than some threshold? Was it greater than or equal to 100, or was it greater than or equal to 0? Depending on the result of that condition, I then need to choose or alter the instruction sequence, and we generically call that branching. And in CPU instruction sets, we sometimes call a branch a jump. Okay, so the two things that are present in an algorithm that are not present in a formula are at least one condition, and the instructions that evaluate that condition, and some form of branching based on the result of that condition. Okay, so conditions and branching go together. And in most programming languages, when we put these two things together, we have what we call an if statement. Okay, which now brings us to this example of an algorithm. Okay. Here on the left, I have something, well, actually, I'm recording this in early January. Got a few months before the deadline comes by, but pretty soon most of you are going to be sitting there staring at a table like this, saying, "Oh my God, how much do I owe Uncle Sam or Governor, or the Governor of New Mexico this particular month?" And we're going to wind up with, most cases, maybe we'll look at a table, but underlying that table is a algorithm or a progressive tax computation. Okay, and this particular table here represents a progressive tax computation for federal income taxes. This is not the current value, so don't use this when you compute this year's taxes. I don't remember what year this is from. This is for single individuals filing federal income tax. Okay. Now the idea here is that each of these rows, and we got 1, 2, 3, 4, 5, 6 of them, represents a different formula. Okay, so the first row is, the formula is 10% of whatever your income is. That's what line find is, period. Nice, pretty simple formula. The one at the end, on the other hand, says, well, if your income is, over 319,100, boy, wouldn't it be nice to be in that situation? Then the formula, rather than being 10%, is $92,592.50. Always kills me how the IRS cares about these 50 cents. Okay, plus 35% of whatever is over 319,100. Okay, so clearly these two computations, the one on the last row and the one on the first row, are different. Okay, they are different formulas. In order to figure out which of these formulas we have to use, we have to know what the value of line 5 is and how it compares to this list of constants in the first two columns. Okay, so the condition is the comparison of line 5, which is income, to the values in these two rows of constants. Okay, the branching is selecting basically which row of this table contains the formula that we should apply. I've taken this example and I've copied it into another document and color-coded it so that we can pick it apart a little more easily. Okay. So here is the Schedule X shown here on the left and the same program we were looking at shown on the right. Okay. And what I want to do is walk through the program and show how it implements what the various formulas and tests that are embedded inside this table. This is mainly for the benefit of those of you who have not programmed before. People who have written programs before, this should be fairly obvious, although you can perhaps use it as a review. Okay, so on the right side we have, as I said before, an old style BASIC program. This is pre-Visual Basic and other types of BASIC, basically from the 60s, 70s, and 80s. So it'd be pretty tough to actually find a piece of software that would run this program. Okay, because we need to know what our income is in order to determine which of the 6 formulas in Schedule X we're going to apply, the very first thing this program is going to do is it's going to grab the value of income from somewhere. So, and in this case, it's input income means it's going to read it from the user. The user is going to type it in at the screen, at the keyboard. Now, obviously, there's other places you could get it from. You could read it from a file. You could, you could read it from a network, but in this case we're just going to type it in. And so the value of income here, the income is a storage location in which we're going to store a number that represents the income, and it basically matches up with line 5 here from your Form 1040EZ that has your taxable income in it. Okay, so what we need to do with that value of income is we need to compare it to these ranges that are shown in the first 2 columns of Schedule X. So if the value of income is between 0 and 7150, then we're going to apply this formula to the right. If the value of income is, say, between 70,350 and 146,750, then we're going to apply this formula here with the orange background, so on and so forth. We've got 6 different formulas, therefore we have 6 different tests. Actually, as you'll see in the program, we really only have 5 different tests, because if we fail the first 5, then by default we wind up with the 6th formula. Okay. The way the program is structured, as most programs are, it's structured to by default run sequentially through the instructions. So if there are no branching operations, if there's nothing to change the order, it would do 10, then 20, then 30, then 40, then 50, then 60, then 70. Okay. So, best way to do this is let's illustrate what happens with a specific value. Let's assume that the value on your line 5 1040EZ is $30,000. So you run this program, and the first thing it does is it prompts you for that value, and you type in 30,000 and hit the enter key, and now the value 30,000 is stored in this variable or in this memory location that we've called income. Okay. First thing we need to do is determine whether this first formula listed in Schedule X is what we want to use. Okay. So the test we want to perform is that value of income greater than 7150? If it is, then we do not want to use this formula. We want to use one of the later ones. Okay. If it is less than 7150, or if it's exactly equal to 7150, then we do want to use the formula that's just a straight 10% tax rate. So if income, which is $30,000, is greater than 7150, then what we're going to do is we're going to go to 50, skipping over this computation in line 30, which represents this formula showed here. Okay, and since 30,000 is greater than 7150, that condition resolves to true. We then go to line 50, skipping over lines 30 and 40. So we wind up here at line 50, which is where we do the test for the second row. Okay, so now we compare $30,000 to 29,050. Now we don't need to compare to 7150 because we already did that back here in line 20. Okay, if we got to line 50, we know the value is greater than 7150 because we already did that test. Now we want to determine, is it greater than 29,050? Okay. Since 30,000 is greater than 29,050, we're going to skip over lines 60 and 70 and go directly to line 80, which implements the test for the third formula. Okay. So now at line 80, we take that $30,000, compare it to 73,050, and find out, no, it is not greater than 73,050. Therefore, we do not go directly to line 110. Instead, we fall through to the next instruction, which is line 90. And line 90 implements this formula, $44,000 plus 25% of the amount over 29,050. And that's what this particular formula right here is. Okay, $4,000 plus the excess income over 29,050 times 0.25. We store that value as tax. Once that computation is finished, we fall through to the next instruction at line 100, which tells us to go directly to line 180. Line 180 is where we output the value of tax. Now it's printed out on the screen where you can see it, and write it into the appropriate line in your Form 1040EZ, and that we fall through to line 190, which is the end of the program. Okay, so this is an example of a program with a series of comparison. These are all comparisons. Okay, and branching operations. These are branching operations that implements the algorithm for computing U.S. federal taxes represented in Schedule X. Okay, in essence, we have 6 formulas from which to choose, and we need to decide which formula based on whether the value, what the value of income is and how it compares to these upper and lower bounds for each of these formulas. Okay, so clearly an algorithm is much more complicated than a formula. In essence, it's not one formula in this case, it's 6, and we have to choose which of the 6. Okay, and of course in much more complicated programs there might be, dozens of formulas or hundreds of formulas, or there might be whole chains of if statements where we go through very complicated comparison and branching operations to get quote unquote to the point we want to be at. Okay. All right, so now we're to the last slide. So why did I spend all this time differentiating between formulas and algorithms? Okay, well, the real reason for picking on this is because, although you may not realize it, the ability to implement an algorithm, which basically means the ability to do comparison and branching, is the basis of what we consider intelligence. Okay, it may not be the only thing that constitutes intelligent behavior, but it's clearly a very big piece of what we consider to be intelligent behavior. And since we, in the 21st century, expect our computers to be smart, okay, or to at least do smart things or mimic smart behavior, this ability to implement an algorithm is a cornerstone or of that capability for the computer to act smart. Okay, let's just take the very simple example here that I've got here. Outside my office, I'm looking at the most recent hospital edition here, the Bill and Barbara Richardson Pavilion. It's on the other side of Lomas from my office, and if I want to walk over there and go visit somebody in one of those rooms, I've got to cross Lomas. And Lomas is 6 lanes of traffic, and yes, there is a stoplight there, although a lot of people wind up ignoring it. The speed limit's 35, but there's plenty of people zipping by at 50 or 50 miles an hour. And so if I'm standing there at that corner or wondering whether or not I want to cross that street and not get run over, I have several tests. I have several quote-unquote comparisons I need to perform. Okay, if I see a car down the way, say up toward Girard, coming westbound, I have to kind of judge how fast it's going. I have to judge how long it's going to take me to cross that street, and I have to decide at that point, do I step out into that street and assume that I'm going to be able to cross it before that car gets there and smacks me, or can I, should I wait? Should I wait for the walk light? There's lots of inputs to that. It's how wide is the street, how fast is the traffic moving, how fast do I walk, am I feeling good today, or am I a little sore from something the other day? Have I got a bit of a limp, but does my foot hurt, how reliable do I think my observations are? Is it a clear day? Can I really see that car and make a good judgment of how far away it is and how fast it's moving? Or is it, kind of foggy or rainy and maybe I'm not so sure? So there's lots of input variables to that, and in the end, there's really only one decision to be made here. Do I cross now or do I wait and, rerun the procedure in another couple of seconds and try to make the decision again? But it's a complicated process, okay, and it's presumably something we would consider intelligent behavior. The instructions that implement the comparison and the branching, in this case the branch is cross or don't cross, okay, and send the appropriate instructions to my legs to get moving. The instructions that implement comparison and branching are sometimes called logic instructions, and they're called logic instructions because we think of logic and intelligence as kind of at least being in the same category. Now, when we talk about a computer, the logic instructions are fairly limited, okay, where, I can think of, let's take a simple example here. I can compare a face to a picture and say, are they the same people? So I've got a picture in my hand, and I'm looking at the picture, and then I look at a group of people over the side, and I say, is any of those, is the person in this picture present in that crowd of people over there? Okay, that's a comparison operation. Well, in a computer, on an individual instruction, the things you can compare are numbers. So, like we did back in the tax example, is income greater than 29050 or whatever the cutoff value was. When you're comparing a picture to input coming in through your eyes and being interpreted by your brain, clearly that's a much more complex set of data and a much more complex comparison operation. Okay, a computer can actually do that comparison, but in order to do it, it's basically got to take the picture, and the incoming image, it's got to bust them up into pixels, it's got to represent each of those pixels numerically, and then it's got to do a complex comparison where it looks at the numbers that represent those pixel maps on both sides and decides if they're similar enough or not. Okay. So when we look at it on an instruction by instruction basis, the logic instructions built into the computer are actually quite primitive compared to what we can do with our brain. But there is a flip side to that, and that is that the computer can execute a large number of those very quickly and very reliably. So yes, in any given instruction cycle, it may only be able to compare 2 integers or 2 real numbers or what have you. But if it can do 2 billion of those comparisons in a second, then it can be fairly powerful. Okay, here's a good example of this, or one of my favorite examples, is anti-lock brakes. I mean, you've got a computer and software built into your car such that when you jam on the brakes, basically, 20, 30, 50 times a second, it's going to check the speed of the wheels and all four wheels, and it's going to see, is one of those wheels moving a lot slower than the other, meaning that it's probably locking up? And if so, before the thing locks up completely and puts you into a skid, it's going to execute an action which basically starts pulsing the brake pressure to that wheel so that that wheel has less braking pressure than the other three and doesn't lock up. Okay, it's going to do that a lot faster than you could do that. Okay, even if you had the right visual inputs that could tell you which wheel was about to lock up, and even if you had 4 different brake pedals that you could manipulate, clearly you couldn't do that 20, 30, 50 times a second. But because the computer can do that, can operate so quickly, it can do something that you can't do, at least not as quickly and not as reliably. Okay, that concludes this set of slides discussing processors and algorithms and formulas and intelligent behavior.